Afternoon, my name is Rashid Kagani, and I'll be conducting a tutorial on steady-state sinusoids. And I'd like to thank Professor Carmen for taking the time to arrange this tutorial. And we have a lovely audience. And I just have one request. As I go through this tutorial, if you have any questions, please do not hesitate to ask, as I'll try my best to address your concerns. Let's start off with sinusoids. A sinusoid is something of the form AM, let's say this cos. So that cos WT plus phi. AM is called the amplitude of the sinusoid. Whatever is inside the brackets is considered the argument of the sinusoid, and this is called the phase, and this is called, W is called the angular frequency. So angular frequency is measured in rads per second. The phase, in this case, is going to be unitless, because whatever enters a function is usually unitless. Usually it's in degrees. So we write, for example, phi is in degrees. It could also be in radians. So if it's in radians, to change it to degrees, you would take whatever is in radians, for example, as a value. You divide it by pi, pi here is 3.14, as we know it, and you multiply by 180 degrees to change it to degrees if it's not providing the problem. But in most of the cases, it will be providing degrees, as we see. The W, as we said, is measured in rads per second, T is time, and W is also equal to 2 pi F. Now, F is the frequency measured in hertz. And if you take 1 over f, you get t. So what does this mean? If let's say you were to graph a sinusoid, you would have let's say something like this, and you know the cos function, for example, starts off at, if this was 0, it has its peak. That AM would correspond to this value. The omega t, for example, so if you have to know this is going to be measured in time. So if you look at one period, so you start from here, you go down, and you go to one top period. This is t, which is equal to 1 over f. So this is sort of a visualization of what a sinusoid is. And we need to explain what a sinusoid is, because we're going to do something called the steady-state analysis. And actually, what enters inside the differential equations or the voltage sources are going to be sinusoids. So it's imperative that you have an understanding of what a sinusoid is before you can do any steady-state analysis. After we have this, now there's some very, very important trig identities that you might need to know, because before we get into the definition of phasors, you will need to know this trig identities. For example, this one. So if we're given, for example, let me even write them down. I'm going to put them separate because we're going to use them over and over again throughout this tutorial. So you're given, let's say, sine WT plus phi is equal to cos WT plus phi minus 90 degrees. The other one is, this is 1, let's call this 1. 2 negative cos WT is equal to cos WT plus or minus 180 degrees. And then C sine WT is equal to WT plus or minus 180 degrees. And then using A1 and, okay, this is 2, let's use this as 3 to be consistent. If you use 1 and 3, you can derive negative sine WT plus phi is equal to cos WT plus phi plus 90 degrees. Okay, all these trig identities can be derived using, for example, you put, for example, cos A plus B, and you got, let's say, sine A plus B, 1 with the minus there, is equal to cos A cos B minus sine A sine B, and then of course look at the minus, we put a plus there, is equal to sine A cos B plus minus sine b cos a. If you use any of these trig identities, you can actually derive all these expressions. And these equivalences are needed because if, let's say, somebody gives you a sine and they tell you you want everything in the basis of a cos, you just have to minus 90 degrees. And somebody, let's say, gives you a cos WT, yeah, there's a minus here. So if somebody gives you, say, a negative cos WT and you want to get rid of this minus, you add plus or minus 180 degrees. And then the same thing for the sine. Sine negative WT equal WT plus 180 degrees. Usually in the problem, you'll be provided with, if you're given something in the form of a cos WT without any negative as a coefficient, you're fine. But if, let's say, they give you a negative, you're going to have to transform into this. And you're going to see this stage how we apply all this. Let me see how 1 and 3, yeah, so 4. 1 and 3 actually are used to derive 4. The reason for this is very easy. You see, there's a negative here. The negative, you've got the choice to transform a negative sign. This is actually a sign, I'm going to point out, okay. To transform a negative sign into a positive sign, you do a plus or minus 180 degrees. So this is your choice. Let us take, for example, 180. Let's use 180, for example, plus 180. And then this will transform the negative sign to a positive sign. Now you want to transform a positive sign to a cos, you minus 90. So 180 minus 90 is 90. So that's how this was derived. So number 4 is also very useful. In fact, most of the time you'll be using most of the time would be, if they want to give you a tricky question, you'll be using 4, and most of the problems that I see in the textbook, you'll be using the conversion number 1. It's used a lot because they're giving you your form of sine and they want you to find things in terms of cos. Okay? So for example, now somebody asks you, this is a very easy question. That's how we always start, easy, and we increase our complexity as time passes by. So you got Vm is equal to, let's say, 12 cos Wt plus 10 degrees. And the question is, what's the amplitude? That's the question I'm asking you. What would be the amplitude? 12. 12 is the amplitude, that's right. What would be the angular frequency? I left it as, you can give anything. To be omega, right? To be omega, and what's the phase? 10 degrees. That's very good. Okay. Now, another question that could be asked, and it happens sometimes we ask this. They give you two sinusoids and they ask you which of the sinusoids is leading and which one is lagging. That's a very good question that you could ask someone. And the question is, let's say somebody gave you V1 is equal to 10, sorry, let me make it more complicated. They gave 10 cos Wt plus, let's say, 50 degrees. And the second sinusoid you're given is V2 is equal to 12 sine Wt minus 10. Let's say somebody gives you this. And then somebody asks you which of these two sinusoids is lagging and which one is leading. And some people have the ability to look at this and give an answer. But for most people, this is a bit challenging unless you do something. You have to actually reduce either sinusoid to a common base. When I mean a common base, I mean either in terms of a sine and in terms of a cos without any negative in the coefficient of the sinusoid. So that's one way to do it. So in this case, if someone told you now you want to transform this guy, let us say cos is our basis. So we want to use cos as our basis. And someone tells you find which one is leading, which is lagging. To get rid of this negative sign, you add or minus 180 degrees. So if let's get rid of this negative sign, this is the same as what? As cos Wt plus 50 plus 180. And then you got rid of the minus 10, there's a 10, plus 10. So we got rid of the minus using which transformation? We use this one, we use number 2. Okay, so there's a 10 here. So if we added, and we had the choice to even do a minus 180, so it doesn't make a difference. And in fact, even all these guys can be verified graphically. Like if you took a graph, this is just an aside before you do this problem. Let's say we looked at this guy. The first one, the sine Wt. What does sine Wt look like? The sine starts off from here, and we go on like this. Now I'm going to draw the the cos. The cos starts off from here, so we go like this. And I don't know if you guys can recall from your calculus courses or pre-calculus in high school, if you see an argument that is a negative, what does that mean? It means it's the original function, but if it's a negative, it means it's shifted to the right. So if we take a cos function, this tells us if we take a cos function without the negative 90 degrees, and you shift it 90 degrees to the right, you will get a sine. And that is actually true. If we take the cos, for example, which is here, and you took it, if you took it, this is cos, yeah, so if you took the cos function, which is this one, yeah, it starts off here. If you took the cosine function and shifted it to the right, it actually is coincident. That's how you can prove this. You can, all these things can be verified graphically as well. But anyway, let's proceed with this one. So you're given negative cos, negative 10 cos, whatever is an argument, and you get that using number 1. Using number 2, sorry. And then now number V2, you're given 12 sine WT minus 10. And the question is, what is this guy equal to? So does anybody have any suggestions on which numbers we can use?
1.
Number?
Number 1.
Number 1, exactly. If we take number 1, we'll go to cos. And if I had a negative, which one would you use?
Number 4.
Number 4. That's right. Excellent. So let's use number 1 in this case, and you're going to get cos WT plus 5 minus 90. But then what do you have to do? Are we good?
12 cos. 12 cos.
There's a 12, that's right. But else are we missing?
5 is 10.
10. So minus 10.
Negative 10, so it's
exactly. So this guy reduces to what? To 12 cos WT plus 5 minus 90 minus 10? Minus 100. And this guy becomes, what's the guy at the top? 180 plus 50?
But isn't our phi already minus 10?
What?
Our phi is already minus 10, so it should just be omega t minus 100.
Yeah, right about that. Thank you for pointing it out. And the first question, what's the, when you reduce this, what do you get rid of that? Can you get rid of this guy and give one value?
230.
230, exactly. Okay, now the question is, how do you compare V1 and V2? We can still compare them right now and to find out what's leading, what's lagging, but the second step would be to compare positives and positives, negatives and negatives. The question is, how can we convert this guy into a positive? So what would you do to convert this to a positive? Any hints?
Add 180.
No, we can't add 180.
Oh, add 360.
Excellent. So you add 360. The reason why we're allowed to add 360 and any multiple of 360 or minus 360, any multiple of 360 is because this is a periodic function. And with a period, 360 degrees. So we're allowed to add 360. And if we do this, what does it become? 260. So now the question is, which is leading and which is lagging? We still haven't solved the problem because now, as we try, let's try to just plot the phases. Forget about the 10 or the 12 because the 10 and the 12, you'll see later when we deal with phases, only contribute to the modulus or the distance from the origin that the complex number is. But so we don't care about that for now. For now, we just care about the phase. So for the phase 1, in this case, is 230 degrees. Roughly 230 degrees will be somewhere here. Okay? Let's call this the V1. Okay? Just the phase. This is, I don't know how to write this down. Let's say V1 phase. And the phase of V2 is 260 degrees, so we'll be somewhere here. V2 phase. Okay? This is an abuse of notation, but please excuse it. It's just for demonstration. Because V1 phase, we saw this was 230, this is 260. What's the difference between these two? Like in terms of phase, what's the angle between these two? 30, exactly. Now the question is, which one is leading and which one is lagging? Now, to identify which is leading and which is lagging, you can't just automatically use the bigger value. No, that's not always the case. What we do is we always look at the smallest angle, the angle that is smallest between the phases. Always, step 1, look at the smallest angle. And then, based on the smallest angle, you can identify the one that is now more counterclockwise is the one that's leading. So you have to establish this first. So when you look at this, the smallest angle is this guy. Based on this small angle, then we say which one is more counterclockwise. In this case, it's the V2. So in case now we say V2 is actually leading V1 by 30 degrees. Now let me give an example where the value could confuse someone. Okay? Just want to do this for a while. Okay. An example would be this. An example would be this and this. Let's say this was 10 degrees. This is not this example. This is 10 degrees and this is minus 10 degrees. Just in case somebody looks at this. Okay. Okay. So somebody looks at this and then somebody tells you, okay, this is, for example, was 1 and this was 2. Minus 10, we want to bring guys to the same thing as 10. So what's another value, another way of saying minus 10?
370.
370. And this is what? This is 10. If you automatically thought, oh, it's the one with the big angle, you'll automatically say, okay, this guy is leading already. It's natural to assume that because now, but the problem is that you're actually using the
350.
350.
350.
Okay, yeah, 350, thank you. So the question is now, you think automatically that this guy is the one that's leading, but that's not the case. Actually, the one that's leading is this guy because you look at the small angle. This is the angle we're looking at. So this is important to do this. You always use the small angle, don't use the big angle. And so far, we haven't covered anything significant as of yet. But this is just all the fundamentals required to understand what a phasor is. Now, we have actually covered sinusoids. Before I proceed, does anybody have any questions about sinusoids? All good, okay. Okay, so what are phasors? A phasor is any number, is a complex number that represents a phasor. I mean, so that represents a sinusoid. What do I say? Sinusoid. Yeah. That's what a phasor is. So, for us to understand phasors, we have to understand complex numbers. Notice every phasor is indeed a complex number, but not every complex number is a phasor. And you're going to see that more explicitly as we go down these topics. So that's what a phasor is. So for you to understand phasors, you need to understand complex numbers. And I'm going to go through complex numbers very, very briefly, and I'm just going to cover what is essential and what's required to understand for the discussion of today. So what's a complex number? Complex number. And good. And dry it out. So a complex number, for example, is a number that has so you can think of it as a two-dimensional number that has both the imaginary and a real component. And the imaginary and the real components are indeed real numbers. Okay, so for example, it's a number of the form a plus b j. We use j in electrical engineering. Unlike mathematics, in mathematics and most other fields we use I. And the reason we use j is because we don't want to confuse it for current in electrical engineering. So that's why we use j. So you realize a and b are real numbers. So plus or minus numbers that you see in the real axis, or the real domain that you are well familiar with. So the only thing that actually is separating a and b is j. It's what's making this guy a different creature from this guy. This is the separating thing. What separates A and the B is J. Okay, that's what allows this to be viewed as a two-dimensional entity. Okay, so it's something of the form A plus BJ. Now we can plot a complex number in a two-dimensional plane. So you can go A, comma B. You notice a complex number is not R2. It's not R2. It can be graphically represented as a number in R2, okay, as an R2 number, but it's not R2. Okay, it's analogous to a vector, but it's not even a vector, so to speak, because there are some operations in the complex domain that you cannot do with vectors. Okay, for example, division. A division of a vector. That's something that's meaningless in the vector domain, but it's meaningful in complex numbers. So don't confuse. Don't automatically think that a complex number is a vector. It can be viewed as a vector, especially when you're adding or subtracting or doing a scalar multiplication. But when you get to other operations, it's not going to be the same thing. Okay? So now we can do something called the real, meaning we're taking a complex number of the form a plus bj, and we are trying to plot it onto a plane. So we're taking the a and we are mapping it as x. We're taking the b and we are mapping it, the b as bj, we're mapping it as just b only. We're assuming the j is implied. The j is here, the somewhere. So we use the word imaginary. Okay, so there's no j, it's implied. So when we use a plus b, we're saying this is a times bj. So if let's say when you pick c, comma d, we're saying c plus dj. This is what the graphical representation is. It's implied. Okay, we don't usually put a j here. We're just talking about the imaginary. And this is real and that's real. So the two components. Okay, so that's what a complex number is graphically. And now we have operations that we need to do. We need to do, let's say, z1 is equal to a1 plus b1j, for example. We've got z2 is equal to a2 plus b2j. And the question is, what is z1 plus z2? And anybody have any hints of how we do this? Any hints?
Add the components.
Which components?
Like the a1 and the a2.
And the
j.
And the reason for this is you're right. And the reason for this is because if you've got a1 plus a2, this is just a number, right? But you've got b1 j plus b2j. What happens is you can actually factor a j. So it's just j into b1 plus b2. So he was right. You just add the dimensional components, just like the way we do vector addition. Look, for example, v is equal to x1, y1, and someone told you v2 is equal to x2, y2. How do you do v1 plus v2? You just add the components. It's just kind of the same thing with vectors in addition and subtraction. So, and by the way, so we did a plus. If I got did a minus, we do a minus, we do a minus, we do a minus, right? So that's pretty simple for addition and subtraction. We can multiply by a scalar, which is very obvious. Just multiply both components by that scalar. So with addition, next is multiplication. A plus bj. Let's use 1 into a2 plus b2j. And someone asks you to find the product of these two complex numbers. What would you get? You would get a1, a2. Look, okay, let me make this much simpler. It's a1 into a2 plus b2j plus b2j into a2 plus b2j. Have I made a mistake? 1, 1, 1. This should be 1, right? Yeah. And then you expand. Now, the expansion so far, this is easier because this is just a1, a2, a1 times b2. So this is just basically a1, a2 plus a1. No need to actually copy any of this because this stuff can be done usually, depending on the problem. You just employ this strategy of just taking one component, multiplying by the second entire, and do the same thing. So a1 times a2, a1 times b2j, yes? But then when we come to this component, it's going to be b1 times b1j a2, right? Which is a2 can be actually brought in front, it doesn't make a difference. This is just the real number. And then now b1 and b2j. I forgot to mention in the beginning what the hell is j. J is actually the square root of -1, for those who don't know.
So the last one is j squared.
Yeah, next one is j squared. So there's a j squared. And then what does a j squared mean?
It's -1.
-1, okay, fine. So that's why it does b1, b2, negative. Now you realize this is a real number. Like this is like 2, 7, -7, right? Whatever. You take this b1 and you combine it. So it's going to be a1, a2 minus b1, b2. And then you take the components with respect to j plus j into a1, b2. I just factored. I took whatever this guy was, I took this guy, and I factored the j. Plus a2, b1, right? Now this guy is now, if let's say you're to write another, this guy in as a z3, this guy is equal to a3, this guy, and this guy is equal to b3. This guy only the number itself. We forget about the j, because the j is here. The j comes out. So you can see how this guy reduces to that, this guy reduces to that. So the sum of complex, the product of complex numbers is indeed another complex number, which does have a real and imaginary component, defined by this. Now this appears very, very tedious, and I do accept it doesn't look that nice. And in fact, when we multiply complex numbers, We don't use this approach. Usually we don't. We are allowed to, but we don't usually do this. What we do is actually go into the complex domain. I mean, to a polar coordinate, sorry. What am I saying? So this is the good chalk. Let's say you got this. You have, let's say, theta. The same how we had A, comma B. Now we say, okay, you know what? Let's come up with a different problem. Let's say, you know what? Let's find this length. This length is called modulus, Z. The modulus of the complex number. AB is actually equal to Z. So the modulus of Z is the length of the complex number from the origin to the point that represents the complex number in the complex domain. Phi is an angle that is like polar coordinates. How do you map a point using polar coordinates? Well, you've got phi as the angle. Here I have theta, but let's use phi. Phi as the angle that's formed from the real axis. Okay, so we can represent the same complex number in this form. And if you were to represent the same complex number A, comma B as Z in this format, what will you say? It's equal to, for example, A squared plus B squared, because we take, it's a triangle. This is A, that's B. So you take A squared plus B squared, you take the square root, that's the modulus, right? And then you won't need an angle. So it will be the angle, for you to find the angle, let's call it this phi. Phi is equal to what? To tan, remember, in high school? Tan inverse what? Tan inverse B over A. But under the condition, if A is positive and is equal to tan negative 1B over A if, plus and minus 180 degrees if B is less than 0. Okay, that's how we find phi. And actually, you might not need to do these details if your calculator is capable of doing this transformation from the rectangular coordinates to the Cartesian coordinates over to the polar coordinates. Some calculators are able to do that, so you might not need to be concerned about these details. And the reason why we do this, we have this plus or minus 180 degrees is very simple, is because your calculator does not know the difference between if both A and B are negative. If both A and B are negative, what you have? You have this, look at this. If this is A negative and B negative, this is A positive and B positive. But when you do tan inverse B over A, and negative, what happens? They cancel. So it's like the same thing as if you did, so for example, tan negative B over negative A is the same as tan inverse what? B over A. But graphically, these two things are not the same thing. You've got one that's here, and you've got one that's all the way here. You see? To distinguish these two, I mean, when you plug this in the calculator, your calculator is always going to give you this value, regardless of whether you're in this situation or that situation. So what you need to do is you need to say, okay, hey, I'm not here. I'm actually, this is my real, this is the truth. This is what the calculator does. This is the calculator does this. The calculator does this, and this is the truth. You're gonna get here. So you go from here, and you have to either add 180 degrees or minus 180 degrees. And this sort of these adjustments that you do, the plus or minus 180 degrees, always happens when B is negative. You can see this is the case. In this case, the truth was you had the negative, right? So whenever you see that you have your x component or your real component of your complex number is indeed a negative, you have to do an adjustment of adding plus or minus 180 degrees. You have to add that to find the phase. I don't know if that, does anybody have any questions so far? Oh, because the whole point is you have to interrupt me if you are. Yeah. Okay. So now we have covered multiplication in the rectangular axis. Now the question is, now that I've showed you how you can transform a complex number from the rectangular coordinates over to the polar coordinates, the question is how can we multiply now in polar coordinates. So let's say, for example, you had a z1 is equal to the modulus, remember? Z was A squared plus B squared, or the square root, right? And then you have got the angle, which I'm not going to represent how you got that. But let's say you got that using the tan inverse, and you always make sure that if your real part is negative, you made an adjustment. Let's say you got this. And then now your question is, now you have a complex number, let's say you've got z1 and you want to find times z2. Remember how we before in the rectangular coordinates it was very, very complicated. But now it's very easy in polar coordinates. But now z, the question is how do you multiply them? Very easy. You actually take the z, and let's say it was z1, z2. So we take the modulus, and we just multiply them as usual. And then we take the phase, so this is phase 1, we do phase 1 plus That's it. Very easy. So so to multiply complex numbers, you just multiply their modulus, and then you add up their phases. That's how you multiply complex numbers. Likewise, if you wanted to subtract a complex number from another, let's say for example you wanted to do z1 divided by z2, in the polar domain, you would say it's equal to z1 divided by z2, and then you would have the phase as phase 1 minus phase 2. Okay, this is the polar domain. This is how we do the multiplication and division of polar domain. And I'll give some examples in a bit, but this is just needed. Now, we talked about, before we talked about, we could represent a complex number as rectangular, and we can represent it in the form of polar, right? The polar form. A rectangle is the same as a Cartesian, right? So this is Cartesian, this is polar. The question is, what are the strength of the rectangular and what are the strength of polar? For rectangular, it's very useful for addition. So addition plus subtraction, this is the way to go. You want to go with this one. Polar coordinates, you can't add or subtract. You can't add or subtract, but not unless the phases are the same, which never happens. You know, most of the time, it doesn't happen. So really, really can't do addition / subtraction. And not unless, of course, phases are equal, which is very rare. Okay? Now everything else, like multiplication, division, this guy can do, but it's not the way to go. It's not recommended. So not recommended. This is not recommended. You want to go with a polar coordinate. This is the best way to do it. Okay. I think I already discussed this way. I discussed this guy. I discussed multiplication, but I haven't discussed division yet. And that's the reason why for this. I've discussed multiplication and division. Multiplication and division, I already discussed this out in the polar domain. Addition, of course, you can't do, as I said. And now, what is that? Then somebody can ask, then why the hell do we use polar coordinates? Other than maybe the benefit of multiplying and dividing, why would you use polar coordinates? Well, there's also another strength that polar has that this guy doesn't have, taking powers. So if you want to take a complex number to a power, this is the way to go. This is more powerful than this. In fact, this guy, I don't think you can't do it. So you can't. So taking powers is the way to go with the polar coordinates, and you don't do that with the Cartesian coordinates. So the Cartesian seems to be more, generally it seems to be more powerful than the polar for phasor computations. Usually it's a way. Other than for division and multiplication, where this is the polar, the strength of the polar is really seen when you multiply and divide complex numbers. Now, I haven't discussed division in the rectangular coordinates. I'm going to do that right now, and then we'll conclude complex analysis. Complex numbers. So before I do this, there's a reason why I left the division last, because it involves definition. So if let's say someone asks you what is z1 divided by z2 in the rectangular coordinates, what is that? And the question is, for you to do this problem, you say, you know what? Why are we doing a two-step problem? Let's do a one-step problem. Let's say we know how to do z1 times z2 as I described in the Cartesian coordinates. And it involves those two expressions multiplying one side of the complex number by the other real and imaginary parts of the other complex number, and doing all that fun stuff. But for you to do z1 over z2, let's reduce the problem to say, let's find what's z1 times 1 over z2. This is the best way to do it. Because 1 over z2, if we find that it's a complex number, then when we get that answer, we can simply just multiply it by z1 as we discussed before. So the question is now, the real question we're asking is what is 1 over z? For any complex number, what is this? This is the question that we need to ask ourselves. Once we're able to do this, we can apply what we discussed before. So what is 1 over z1 of a complex number in the rectangular coordinates? So you've got 1 over a plus bj. This is the same as 1 over z, where z is equal to a plus bj. Right? It's this. Now the question is, how do we deal with this? Well, we just multiply it by its conjugate, a minus bj, and a minus bj. We take these two. This is from the algebraic expression, x squared minus y squared is equal to x minus y into x plus y. Okay, this is, we all know this. So we apply this to this. If you can, in your mind, visualize that x as a and a y as bj, not just b, bj, then we can say this is equal to what? To a squared, right? Minus what? bj, all what? Squared. A squared minus b, what's j squared?
-1.
-1. -1 times negative is?
Positive.
Positive. So this is equal to a squared plus b squared. And does anybody, can anybody relate this to how we describe a complex number in the
Modulus?
Exactly. It is the modulus
Squared.
squared. Excellent. This guy is equal to z squared. Very good. So, and then, so in the top, this guy is going to be still a minus bj, right? So it's going to be still, I mean, this guy is still going to be a minus bj over this. Now, this is good because this guy a number, a complex number, which is a real number or a complex number?
Real.
Real. That's good. So we can take this guy and remember how we said a constant can multiply both the real and the imaginary parts. So if this guy you reduce it to maybe 6 or 7, you can just do, and this guy let's say was 2, to be 2 over 6, and you reduce it as a final value, right? So you can actually find the one value and the coefficients in terms of a or b, if it represents a complex number as a plus bj. So you can actually find a value here and a value here, which is no problem without the denominator. Now, the question is, what's this? What's this guy? We haven't defined him. This guy is actually very, very significant, and it's useful to know what this guy is, because when you come down to the maximum power theorem, we'll find out that a minus bj means something with respect to a plus bj. A minus bj is called the conjugate. Graphically, what's this? Graphically, this is a representation, let's say about a complex number here. What is it graphically? If let's say this was a real, this was imaginary, which is, this is customary how we always represent complex numbers. Anyway, we've got a, b, minus bj means what? You take the b and you do what?
Reflection.
Exactly, reflection. It's a reflection about the real axis. So you've got a, comma, minus b. That's what, and this is the conjugate. So the conjugate is a reflection of a complex number about the real axis. That's the guy. And a squared plus b squared is the modulus. So let me just get rid of all this explicit notation and make it simplified very, very easy. We say 1 over z is equal to z conjugate. This is the notation to represent conjugate, divided by z modulus, not modulus, but what? Modulus squared. This is a very fast way of finding what the reciprocal of a complex number in the Cartesian coordinates. So what you just do is just take the modulus, find the square of it, find the reciprocal of that value, and multiply it by the components of the conjugate of the complex number, and you'll get the answer very, very quick. So for example, if somebody gave you 2 plus 3j, if you wanted to find what the reciprocal of this guy is, this guy is equal to z1, and you wanted to find what is 1 over z1, quickly, in Cartesian coordinates, you just say what? It's 1 of what? 2 squared plus 3 squared. Then you do what? You do a square root or leave it as is. Do I do this or do I leave it as is? That's the question I'm asking. What's in the denominator? Do I square? Exactly. So do I put the square? Do I leave the square root or get rid of the square root?
No.
There should be no square root. Exactly. So it should very easy. So it's just 2 squared plus 3 squared. That's actually a positive number. And then you take the 2. And what's the conjugate? What do you do with the 3? You do minus 3j. Okay. And if let's say you had even an expression as f of z, as a function of z or z, and somebody told you to find the conjugate of this guy, what you would do is you actually go into your function, and anytime you see a j, you put a negative in it. That's a rule of how to find a conjugate of a complex function, for example, but that may not be needed in this class. Okay? So the only thing that you need to do, and you need to know how to do very, very well, is to go from polar to Cartesian, and go to, from polar to rectangular. This is what we're very familiar with. Rectangular or Cartesian means the same thing. To go this way, and you need to know how to go this way very quick if you don't use your calculator. Sometimes it's very easy. If you look at your calculator, there's some functions that allow you to do this. They allow you to change from polar to Cartesian and Cartesian to back very easily under one operation. But for those people who don't know how to do that, or are not interested, or don't have calculators that have those capabilities, you should be able to do this by hand. And it's not even that difficult, to be quite frank. The only concern is, remember I talked about how you can go from, did I talk about how to go from polar to Cartesian? No, but I did talk about how to go from Cartesian to polar, right? So how do you go from polar to Cartesian? This is a very good point. So let's say I've got this and phi 1, how do you go from this guy to this guy? Well, it's very easy. You just go r cos theta 1, comma, r sine theta 1. And the reason why this works is because of Euler's formula. And Euler's formula says e to the power j theta is equal to cos theta plus j sine theta. This is what Euler's formula is. And theta is just a dummy variable. It can be anything. And this can actually be proven using the Taylor series expansion. So if you take the Taylor series expansion of the complex exponential, e to the power j theta, and you take the Taylor series expansion of cos and the sine, and the cos is really the expression of the cos in terms of the Taylor series is of the form, let's say it's an even function, so we start off with 1. So it would be 1 minus theta squared over 2 factorial plus theta power 4 over 4 factorial, and you keep on going. And there's alternating plus and minuses. And there's sine theta without the j, let's take the j outside, and this would be, sine theta would be, it's an odd function, so we start off with x minus x power 3 over 3 plus x power 5 over 5 factorial, 5 factorial. And you keep on doing this. This is the Taylor series expansion of the sine. If you take this guy and you multiply by the j's, okay, you multiply this by the j's, you would realize it's equal to this guy, because this guy without the j, is going to be, without the j is going to be 1 plus x squared over 2 factorial plus x power 3 over 3 factorial. This is without the j. This is if this was theta. So since we have to substitute x for j theta, you just get rid of the x and put j theta. Get rid of the x and put j theta. This expression should be valid. You could verify this using the Taylor series expansion. But this is not needed in class. This is just as a convincing argument that this is true. So, before we talked about the polar coordinates and we talked about the Cartesian coordinates, now there's another way to write a complex number in this form. Like, remember how we said e to the power j theta is equal to cos theta plus sine theta plus j sine theta? By inspection, you can say that, okay, this cos is actually the real part of the number. The sine is the imaginary part of the number. This is under the assumption that the modulus is 1. If the modulus was 1, let's say the modulus was, let's say, 6, for example, you have to multiply 6, you have to multiply 6. So 6 times this guy would be the imaginary. 6 times cos would be the real part. So this is another way of writing a complex number. So I want you guys to see the connection. The connection is here. So if you have to write a complex number in this form, this is called the complex exponential form, or they call it what? Another way they call it is exponential form. Let's say you call it z e to the power j theta. Using Euler's formula, this is the equivalent of writing with the polar way, which is the same way as z, right? Modulus of z angle phi. So these guys mean the same thing. I want you guys to commit to this interpretation. It's very easy. It means the same thing. Nothing changes. You've got a j, but now there's no j here. Okay? Okay, so I know I haven't covered complex analysis very well, and I sort of like rushed it. And the reason for this is because I did this already a lecture and also a video tutorial on complex numbers, and I want you guys to go look at those videos as a reference. Actually, I think it's covered quite thoroughly in that video. This is just as a warm-up for those people who, who just need a warm-up on complex numbers. So this is a thorough overview of complex numbers. I mean, it's a big field. Some courses they cover the complex analysis in more than even 2-3 textbooks. We're just covering, let's say, this is just basically purely definition. So the question is now, what is a phasor? So we covered complex numbers, so now we want to know what a phasor is. And remember, the definition of a phasor is it's a complex number that represents the amplitude and the phase of a sinusoid. So let's say you've got a sinusoid, AM cos WT plus 5. And the question somebody asks you, can you please find what is the complex representation? Meaning, what is the phasor representation of this sinusoid? What is the phasor of this sinusoid? So, does anybody have any hint on how I would do that? What would be, how would I represent this guy as a phasor? I don't expect any response because we haven't yet defined what a phasor is. So if let's say you're given AM cos WT plus 5, it would be the real, this is what the definition, you see, that's just the definition. VM E J phi e to the power j omega t. Okay, let's just stop here for a while. Let's just look at this for a while. E to the power j theta and e to the power j omega t, what's this? This guy is equal to what? When you have a to the x to the power n times x to the power m, what's this equal to? Forget about this for now. What's this equal to?
X to the n plus m.
Excellent. Now, we come here. We treat E and E are the same b's, right? So we can add exponentials, yes? So we do the same thing. We got Vm e to the power x plus 5 plus, then we just put them as one factor, j into what? 5.
Plus 5.
Exactly. Okay, we still haven't done anything yet. This doesn't mean anything. And then you've got real, okay? Vm would represent what in this case? Remember how we did the complex exponential? Remember we talked about a complex number can be represented as, I just discussed this, as z modulus e to the power j theta 5. And this is actually what? This is analogous to what? Or actually it's equivalent of z modulus. Remember how I said this was equivalent? Now if you to graph this guy, what does this guy look like? This guy looks like what? You have this, you've got 5, and you've got z modulus. Yes? And this is the point that represents a complex number, yes? This is this guy. And this is also this guy. It means the same thing. So the question is, what is this guy? So what's the phase in this case of this complex number? What's the phase of this complex number?
5 plus omega t.
Exactly. It's the equivalent phase is 5 plus omega t. That is very true. And if we take this guy to be the real, remember how we apply Euler's formula? Then in this case, what's the real part of this complex number? How do you write the real part of this complex number? What do you mean? If let's say, let me make this very easy. If let's say somebody give you z e to the power j theta, and somebody asks you what is the real and imaginary parts of this complex number? How would you do it? Forget about this for now. Forget about this. What's the real and imaginary parts of this complex number?
Z is the real.
No, z is not the real. Z is the modulus. Remember? So it's not z. Is not z. Z is not the modulus. Z is just the modulus. What would be? What's the real? Okay. Can we express this in rectangular? Maybe that makes it easy. How do you represent this in rectangular form?
Would it be the components of Z that are there?
Cos phi.
Cos?
Cos phi plus I sin phi.
Excellent. And with just alone or?
So cos phi would be.
No, you're right.
Oh, what times the modulus?
Times the?
Modulus.
Modulus, exactly. So this is actually equal to e to the power, so it's equal to z cos, right, that's very good. And you expect that, okay, plus z sine phi, and then there's a j, right? Yes? So z times j. So this is true, you're right. And this actually comes from Euler's formula. I mean, remember how we talked about cos e to the power j theta is equal to cos theta plus j sine theta? Remember we talked about this? How this guy, if you put a modulus in front, it multiplies both components. So that's very good that you came up with that. So the real part is what now? In this case, if it represents complex number, remember, and then it's supposed to say this is equal to a plus bj. So what's the real part of this complex number? A. And A is what?
Modulus cos phi.
Exactly. And what's the b? Does the b include the j or not?
No.
No.
So it's
It never includes the j. Because the imaginary part is still a real number. So the b is equivalent to okay. So now, the question now we still have to proceed with, we still haven't answered the question. The question is, what's the real part of this guy? What's the real part of this guy? What's the real part of this guy? So it's going to be what? Vm?
Cos omega t phi
Cos-
times Vm.
Exactly. Cos omega
Omega
t plus
Phi.
phi. Do we take the j in? No. Why not? Why did we take the j in? Because remember this representation? When you go from this representation to this representation, there is no j. Right? So we're going from this representation, this is just a complex number. The j does not exist when we find the real. And we find the imaginary. There's no j. This guy disappears, we just have the argument. And this is very important. We go from here to here. Now, you realize this was original. Remember original? And sorry, this guy was Vm. Well, this is supposed to be Vm then. So we can see this, right? Right? Now there's an equivalency, yes? Now, the question is, what is this guy? Now, somebody said this has already been defined. Somebody has said, you know what, by definition, now this is what we define as the phasor. Okay, that's a phasor. The phasor is a complex number because e to the power j theta is a complex number, right? It's just this guy, right? It's a complex number and the modulus of z is actually Vm. So it's a complex number that represents the amplitude and the phase of a sinusoid. That's the definition. Okay? So we're going to now that we know this, the question is now, let's do it using practice because theory has its limitations. Let's talk about practice. I'm going to give some examples and I'm going to ask you guys to give me what the phasor is, okay? And this is very, very important that you be able to do this very, very quickly. So somebody gives you Vm cos Wt plus phi. And somebody asks you, this is the time domain, this is the phasor domain. Somebody asks you, can you please convert this guy into a phasor? How do you do that? What's a phasor representation? Okay, I'll do one example, okay? So then you guys can see. If there was a Vm here, it would be Vm, remember the amplitude, and
E to the phi.
you can use e to the j phi. You can use that. That's right, but let's use this notation. Okay, what would that be? Phi. That's simple. Very easy. If you could actually even write this as you have the right to say this, it's equal to Vm e to the power j phi, because these two notations are equivalent. But usually by convention and in your textbook, we always use this. Okay, so this should be easy. Okay, let's do another example because it might to drill this concept in. Let's try Vm is equal to 30 cos Wt plus 20 degrees. Can you guys give me the phasor representation?
30 angle 20.
Yes. Remember, the idea is we're just trying to represent the amplitude and phase of a sinusoid. It's really that simple. Okay, now the question is, somebody gives you, now let's try the other way around. Somebody gave you 10 5 degrees.
10 cos omega t plus 5.
Exactly, 10 cos omega t plus 5 degrees. You realize the phasor has does not have the ability to contain the temporal information. It is time independent. So it's implied. Whenever we deal with a phasor, in our back of mind we think there is a j, and there's an omega t. That when we convert from the phasor domain into the time domain, we will now have to put the omega t. So that's what distinguishes actually a phasor from a complex number. When you deal with complex numbers, we don't have something lurking in the back of our mind that when you go back to the time domain, we're going to put omega t. There is no that when you deal with complex numbers. So somebody gave you this, someone told you this is not a phasor, this is a complex number. Then when you go here into this domain, there is no what? There is no cos, there is no omega t, it's just a complex number. Okay, a complex number can exist in either domain, it doesn't matter, but a phasor, you have to know the difference. So every phasor is indeed a complex number, but every complex number is not necessarily a phasor. This is distinction. Okay, now that we know what phasors are, complex numbers, we call it phasors. Next is just impedance. Okay. So does anybody have any questions so far? Any questions? if you want me to go through a multiplication, division, addition, subtraction, using polar coordinates, using Cartesian coordinates, just let me know. Anything. Okay. Just the last one before we take a break, if you guys want to take a break, is before we do that, is let's talk about what is impedance. Impedance. The question is, what's impedance? Impedance, I think that's spelled. Okay. So, in the time domain, initially the impedance was purely resistive, only had resistance. In the complex domain, you could have something else. It is actually the special case of the AC circuit or AC analysis. A special case is DC, so to speak, with respect to impedance, because the impedance on the DC was purely a resistor, only a resistor, right? The impedance generally is of the form, we actually call it Z. That's what we do. Z is equal to R plus X J. That's how we call the impedance. Impedance is kind of like the resistance equivalence in the phasor domain, or in the complex domain. And the question is, what's R? R is a real number, and also J is a real number. And the question is, what's R? R is, just you guessed it, is equal to what? It's what? It's resistance. But what's X? X is something called reactance. Okay? So it's the imaginary component of impedance is called the reactance. And the question is, how do you find the impedance of some circuit components? And this is essential that you know how to do this very, very quickly, actually. So if somebody gave you a resistor, and they told you what is its impedance, can you guys take a guess what that would be? So this is the time domain, this is the regular DC, and now we're going to AC. So for example, let's go DC, this is AC. What does a resistor translate into on the AC? Does anybody take any guess? Just take a guess.
A resistor.
Exactly, it's still a resistor. And nothing changes. But now we're given now a capacitor, and we're given an inductor. And the question is, we're trying to find out what is the impedance. So the impedance is actually defined in the complex domain as V. Remember how I got V equal IR on the DC? This was DC, right? On the AC, it's actually V is equal to, I'm going to use the word, I'm going to just use phasor notation. I as a phasor, and R. R we use Z. This is this. So impedance is actually Z is equal to V. I'm just going, this is just phasor notation, for example. It's not conventional. Maybe it's an abuse of notation in this course, but just take it as is. It's the voltage divided by the current in the AC domain. That's what impedance is. Okay, it's impedance. I mean, it's what impedes the circuit, or what damps the circuit. It has imaginary, it has a real component. The real component we established is called resistance. The imaginary component is called reactance. Now X could be a positive and could be a negative. If it's a positive, we call this inductive. Okay, and you will see the reason why this word is used. And if it's a negative, we call it capacitive. Okay? And you will see why this is the case. And I'm going to just do that very quickly to show you why this is the case. Okay. So, remember in the time domain, I don't know if you guys recall this, and I'm going to assume that you can remember this. I equals to what? C dV dt. That's the case, right? In the time domain. This applies to what? A capacitor. You can see here. This is a capacitor in the time domain. I equal C dV dt. The question is, now, when this is a what? Can somebody tell me what's this? What do you call this in mathematics? This expression. What's this called?
Differential equation.
Differential equation. What order is it?
First order.
First order differential equation. And the question is, for us to find the solution to this differential equation, you could try many things. There's many, in fact, many solutions to this differential equation, and there are many basis functions that actually could satisfy this. You will see under AC analysis, we actually assume e to the power j theta as our basis function. And it actually works out quite well when our sources are sinusoids. This actually works well. In fact, e to the power j theta satisfies this differential equation, and it actually would satisfy any complicated differential equation of a complicated circuit in AC, under AC, with sinusoids as its input. And this basis function actually would satisfy that differential equation. And it's the reason why we call it steady state analysis, because there's also a transient solution that satisfies it, but it decays with time, and we ignore it because it decays with time, and so, but only the steady state dominates the circuit after some period in time. That's why we use e to the power j omega as a basis function. And so when you use the e to the power j omega as a basis function in this particular case, let's try it. What do we get? Let's try using e to the power j omega without any constants for now. Let's just use it. What do we get if you try this? Let's plug it in here. Let's use sine as that. What do we get? So let's try the v. The v is equal to e to the power j omega, right? So let's say that v equal to what? E to the power j theta. Okay. Let's use an example. When we take a derivative with respect to, there's a time. Let's say there's a time dependency. Okay, because there's omega t, e power j theta, because this was a phasor representation. Okay, let's say that was the solution. So what will this guy be if we take a derivative? How do you take the derivative of voltage with respect to time? Does anybody have any idea? How would we do this?
With respect to t,
With respect to t.
it would be omega e.
Yeah, in fact, let's even get rid of the phase. Let's make it as j omega. How about that?
Yeah. So it'd be j omega
Uh-huh.
e to the power of j omega t.
That's right. This is v prime. Okay? And then now, we assume this was your v, right? And now we got our I. So our I is equal to j omega e to the power j omega t, right? Yes? This is our I. Our I of t is equal to this guy. What was our v of t? E to the power j omega t. Now, can we represent, or how you say v equal IR? V is equal to what? I z in the complex domain. So we take v over what? V over I is equal to z. There's no v equal I. So let us try to represent, to find out what the z, or the impedance of a capacitor is. So we'll take this guy. We'll take the voltage. The voltage is what in this case? The voltage we assume to be what? To e to the power j omega t. So e to the power j omega t was our voltage, remember? And what's our I? J omega e to the power j omega t. So we've got j omega e to the power j omega t. What happens? This is equal to z. What can you do to solve, to reduce this further? You can what?
Was that jw? So that would be the e to the jwt would equal 1.
Yeah, so
1 over jw. Wait, 1 over
exactly,
jw.
right. These two cancel. That's z. Z is equal to 1 over j omega. Using this same principle, this is just the derivation, but in fact I'm not supposed to go through this tutorial, but if you do this again for the inductor, and you do it for, this is the law that governs the capacitor. In fact, it's because of this guy that we can conclude this.
That's the general level. We would include the c as well, would we not? For I equals c.
Yes.
dt.
So in fact, there was a
We would need to multiply the e by c.
There was a c. Yeah.
We've just done the general without
You're
c.
right. You're right. There was a c. There was a c here.
Yeah.
In fact, you're right. It's because I like that because you pointed out j omega c. I don't know if you guys have seen this before, but that is actually the impedance of a capacitor, 1 over j omega c. It's true, and it's purely, it only has a purely imaginary part, which is indeed. Remember how I told you if the imaginary part of the impedance is negative, we call it capacitive. Well, let's multiply by j. What do you get? J times j. What do you get? This guy?
Negative.
Negative. That's why it's negative. That's why we call it capacitive. That's the case. Thank you for pointing that out. Very good. So omega and c. So what does this tell you? It tells you that the impedance of a capacitor is actually dependent on what? On the operating frequency of the circuit. So if you're given an operating frequency of a circuit, you can actually find the impedance, given that the capacitance is given in the problem. So using the same trick, you can actually, you can derive the one for an inductor, because the inductor, the law that governs an inductor in the time domain is what? Does anybody know? What's a differential equation that governs the behavior of an inductor in the time domain? I'll just give it to you. V equal to L di dt. We know this, right? So if we do the same thing that we just did before, we would conclude that the impedance of an inductor is equal to what? J omega L. Okay, we do the same thing, we get this back. Okay? So now, once you know this, now we're in a good shape, because that was actually the most theoretical thing that I was going to cover today. There's no more theory after this. After this now, everything should be sailing. You should be sailing through. So we have an element. It's the table that's going to summarize everything that you need. We've got the time domain, and you've got the frequency domain. This table is very, very essential. So you've got the resistor, you've got frequency domain, the relationship in the frequency domain, and then we're going to call this, let's call this the impedance, okay? Impedance, or Z of the thing. So we've got the resistor. The resistor in the time domain is what? The established before is what? The resistor. Is the time domain, it's a resistor. And the relationship, the Ohm's law in the time domain is what? Is V equal what?
V equals IR.
V equal IR. Also V equal IR here, but then the relationship that actually governs this element, let's say an inductor is equal to V is equal to what? L di over dt. And I is the same to your function. Could be a function of time or not, but let's take this L di dt. And then you've got C is equal to I mean for the capacitors, I is equal to C dV over dt. This is so far the relationship. We can use Ohm's law and for the resistance. And then now in the frequency domain, nothing changes for the resistor. It's still, I mean, we still have V equal IR. I don't even know why the textbook has ZR. But anyway, for the inductor, we have, remember we said Z is equal to what? The relationship would be V is equal to J omega Li. J is a complex number, omega Li, I is a phasor, so these are the phasors. And in the capacitor is what? Is J is equal to 1 over J omega Ci. This is I. Okay? So we can deduce now the resistance, the impedance of a resistor is R. This is the most important role that you need to focus on. The impedance of an inductor is what? Using this. V equal I/Z. So Z is equal to V over I. And let's say we're dealing with the phasor representation. So what's this? This is V. So what is the impedance here?
J omega L.
J omega L. What's the impedance here?
1 over J.
1 over J omega C. This is in fact, I can't even highlight this point. This is what you're going to be using for this course. And the reason why I went through all that rigorous theoretical background information is because you could ask, where does this come from? So I hope I satisfied that, those kind of questions, your curiosity on that. So this is really what you need to be concerned about as we proceed. This is the most important thing that you need to focus on. Because in the frequency domain, this is how we find the impedance. In fact, if you should memorize this should be memorized automatically. Okay? All the time, know this. Okay? It's essential, but that's the most important thing. Okay? This is for a resistor, an inductor, a capacitor. And this is another way to represent this is you get rid of you can multiply by J, the top and bottom, and you get what? A negative, then we have a J. This is another way of writing it. I can't emphasize how you should only focus on this mostly. Then I'm not saying this stuff is very important, but I'm saying please just try to focus at this stuff and memorize it. This is, I think, very, very essential. Because sometimes some students say, I don't know the formula, and then they go and they try to look for a formula for the impedance, and this is a very easy formula to remember. And you're wasting so much time in an exam if you can't recall this. You should do enough examples such that you're able to do this very quickly and know that. Memorize that by heart. Okay, so now there was just another thing that needed to be, you need to also know one thing in the frequency domain. And we're talking about steady state. And the question is a capacitor, for example. After time has passed by in a capacitor, the question is how do we find the voltage between a capacitor after time has passed by? What can you guess? Anyone take a guess? What would be the voltage across a capacitor after time has passed by? Let's make it a much more simple question to ask. What is the current that flows through a capacitor after time has passed by? What's current? What's the current that flows through a capacitor after sufficient time has passed by in DC? I is equal to C dV dt. The voltage is considered DC, is constant, so the derivative of a constant is 0. So yeah, the current is 0. So it's a current, so under DC, let's see AC and DC and AC. This is important that you guys know this. So for a capacitor, it behaves under DC like what? As after sufficient time has passed by, it's an open circuit. In fact, we can even leave it as that.
So it's completely saturated.
Yes, exactly.
So no longer any current can travel through.
That is right, because all the charge has saturated in the plates, so no more current can actually flow. Okay, and so on the AC, actually, let us see, on the high frequency, remember how we talked about 1 over j omega c? So on the high frequency, what would be the impedance of through a capacitor, for example? Let's say omega is very, very high, 1 over something that's very, very big is what? 1 divided by W, W is very, very huge, what do you get?
0.
0. So this, and this is the what? This is the impedance. So if the resistance or the impedance is 0, what does that mean on the AC, on the high frequency? Let's use high frequency. How does a capacitor behave on the high frequency? Short circuit, right? And explain, because number 1 over j omega c, omega is very, very huge. 1 divided by something very, very huge is very, very small. That means the impedance is small, or close to 0. If the impedance is close to small, that means we have a short. And you can use the same argument and you'll find out that for an inductor, you have short under DC, which we know, and it's going to be open under AC, high frequency. This is something that you might not need to know, but I would want you to please never forget the one for the DC case, because you're going to see how it's going to be seen in the exam over. This at least you should not know. This is the most fundamental actually. This is after the transient response has died out, under the steady state, the capacitor operates as under DC as an open, the inductor as a closed. After the circuit has saturated, that's what this is the case. And AC is a different story, and we should explain the reasons why. Okay? Okay. So, the last question, before we take a break, this is the last question. The question is find the impedance of this circuit. I'm trying to go through this as quick as we can. Yeah. Somebody tells you to find the impedance across this circuit, this network. You're given a network here, and you're given this, and you're given a capacitor. And then you got, you put that resistor, you got the capacitor, and then you go back here, then you have this, you got the inductor, and you go here. And then somebody's asking you to find the equivalent impedance as seen with respect to these references, A and B. Somebody's asking, can you please tell us what the impedance as seen from these two terminals? Of course, you have to ask, you have to say, you have to give me values. So we say 0.5 microfarads as a capacitor with an 8 ohm. This is the last thing we do before we take a break. And then the capacitor here, let's say, got 1 microfarad, and you've got 8 henries as an inductor, and this is also another inductor. I mean, sorry, this is a resistor. So sharp. So this is 200 ohm. And the question someone is asking, can you please tell us what is the impedance as seen from these two terminals? That's the question that's being asked. And the question is now, for you, when you look at the circuit, you have to, the first question that should run through your mind is saying, hey, you guys are giving me capacitive values, and you're giving me the inductor values as in Henry and farads, and since I don't see an operating frequency and I need that clearly, you see, I have W, omega, right? That's operating frequency, operating angular frequency. So you're given this and somebody's telling you, hey, I can't do that, I can't do anything until you tell me what omega is. So in this problem, omega is given to you as 10. Notice, if they didn't give you explicitly 10, they gave you, let's say for example, a sinusoid, which is listed as cos omega t. Let's say they give you 5t plus 6 degrees. Let's give you an example. In this case, what should you do? You would take, exactly, you would take the omega from the cos function. But in this case, we didn't give you that. But this is a good point that you have to know. So, you don't know what omega is. Omega is 10. Somebody told you what omega is 10. You multiply 10 by the inductance and multiply by J, and you're going to get Henry. So, can somebody please tell me what this gives me to be? If you use those formulas for impedance. Just take it. No, you don't have to give me a real value. Just give me an expression. I mean, the value is meaningless. You just want to know the method.
J 10 8.
Yeah, 10. J 10 times 8. That's it. Okay, for the resistor, does it change? No. For the capacitor, it would be what? It would be 0.5 over what? What's M?
No,
what does M mean?
Milli.
Milli. So can you give me scientific form? What's that mean? Times 10 to the negative 3. Excellent. This is good. You've got. First of all, let's write down this as 1 over geometry. So it's
This is 1 over
1 over what?
J.
Angular is what? 10.
10.
6.5. 0.5 was it?
0.5
Yeah.
times 10 to the negative 3.
Yeah, 0.5 times 10 to the power negative 3. And same thing, this guy, 1 over
J.
10. I say mistake, but nobody has pointed out anyway. But times 10 to the power times 10, yes. What's gone? 10, yeah.
Times 10 to the negative 3.
10 to the power negative 3. That's it. You guys are saying that. There's still something that's missing. Remember, you put the J on the top. These are J, and these are J, right? I mean, the J is the bottom is right. But sorry, this is right. But we usually don't like expressing it this way. We always like to have the J on top. So we put the J. What should we do here? Negative. So usually this is how we generally represent it. Any other questions? Yeah, and the question is now, how do we proceed from here? How do we reduce this to an equivalency? This is just step 1. Now you guys have to understand that in the AC domain, not all the resistances are given to you. The first step is to find the impedances, which we see it's a bit troublesome, but you know, of course it rips. It's more beneficial to do this than to calculate this problem in a time domain, which may not even be solvable. Okay, but you can see that unlike what you guys did in the previous chapters, this is a bit more difficult to do. So once you find the impedances. Now the next step is how do you find equivalences. Remember how in chapter 1 and chapter 2 of your course, when you dealt with the resistances, you could treat this as a resistance and as a resistance, and this is a resistance. And the question is, how do we transform this over as an equivalent resistance? So the question is, what do we do on step 1? Now I want you guys right now, after you've done this step, to visualize each of these components as individual resistances. Okay, but actually impedances. So you should think of this block as, for example, as Z1. This block as Z2. This block maybe as Z3. In your mind, think of them as black boxes. Then this as what? As Z4. And you see, I couple these two together, but I don't have to. I could make it call it Z4 then the Z5. It doesn't make a difference. But let's say we have it this way. Then now in your mind, you should now substitute Z as R, and you apply the same thing that you did in the first 2 chapters. So the question is now, how do we reduce the circuit? I'm not going to write down the actual values because it's pointless. In the interest of saving time, you can just now
Compress the circuit by adding series and parallel.
Exactly. So I just need you guys now to follow through and give me like the steps. So
Z1 plus Z2.
Z1 plus Z2, this is a series.
Yeah.
Done.
Parallel with
Parallel, this exactly. These 2 components, parallel.
Series
and the last one will be in
And
series.
the last one would be in series. You're right with this guy. And with the series, with this component, with both components, doesn't make a difference. Yeah, exactly. So you guys want to take a break? Feel free. Initially, now we're trying to solve the circuit using something called steady state sinusoidal analysis. So the idea is we have voltage sources that are sinusoids, which we already covered what sinusoids are. And we're trying to find the response of the system under a sinusoid. And the reason why sinusoid is very useful is because you can take, if let's say you really have a sinusoid, let's say you had a periodic function, you can use a Fourier series and represent any periodic function as a sum of sinusoids. And so each of those sinusoids has an amplitude and a phase, and you can apply this procedure using the Fourier expansion and find the response of the system using superposition. So you can take any signal that's continuous, find the Fourier representation, and then apply each of those terms in the Fourier series into the circuit and get a response. That's the reason why we use, one of the reasons why we use sinusoids. Another reason is sinusoids are very easy to work with. They've got derivatives, they've got integrals, they're smooth functions, so they make our life a lot easier. Now, most of the students could ask me right now is, when we want to find some solutions, and you're going to ask me, somebody could ask me a very good question. Where are the initial conditions that we used in the previous, when you did the previous chapters, you had differential equations, and they gave you the initial conditions. And the question is, somebody asked us, why don't we have initial conditions under steady state analysis? Does anybody have any answers to that? Think of anything, any reason why we don't have initial conditions, why we don't use initial conditions like we did before?
The constant. We're dealing in constants. Time.
We're dealing with constants? No, that's not the reason.
It's constant.
No, that's not the reason. We realize we have a cos as an input, and we realize that the differential equations that govern the behavior of the capacitors and the inductors, and depending on the order of the differential equation, if let's say it's a 2-degree differential equation, then you expect 2 free parameters, and the only way to map a continuous, a general solution to a specific solution is you have to find the 2 unknown. You have to know the 2 unknown constants, and the only way to do that is you have to substitute 2 initial conditions, solve for the general parameters, and you get a specific unique solution. And the question is, why don't you have initial conditions under steady state analysis? The reason for this is, steady state analysis does not say that this is the true full solution. No, it's saying this is a solution of the circuit after sufficient time has passed. Let's call this T bar. It is the solution of the differential equation. It's what satisfies the differential equation after sufficient amount of t. It also satisfies the differential equation at any time t, but there is also a transient response that we should add to the solution that is in fact where these initial conditions come in. So there's a transient solution that we should add to the steady state solution to give the general full solution. And it's the transient solution that actually takes in this initial condition. Okay? And we ignore it. The reason why we ignore the initial conditions is because the transient solution is assumed to decay for sufficient amount of t with big O notation of e to the power negative alpha t, if you guys know big O notation. Or we can say that the transient solution is of the form, let's say t of s is equal, t is not a good expression, let's say f of t, but this is a transient solution, it's of the form e to the power negative alpha t, whatever. And the problem is it decays with an attenuation constant. So that's why we ignore it. So steady state solution is a solution where we have where the solution has saturated, or for a sufficient amount of t. Okay, that's when the steady state is assumed to have decayed. Of course, the steady state, the transient solution only decays after sufficient t. And usually when t is at infinity, the transient solution is indeed 0. So the transient solution becomes realistically 0 after time infinity, but you don't have to wait for time infinity. For even a sufficiently small t, we realize that this guy could be even 0.000 of its initial value. That's why we ignore the transient solution, and we only focus on the steady state solution. Okay, so this, another thing you have to be cautious about is this steady state solution only works for sinusoids. So if you didn't have a sinusoid, you can't use this method. You will have to go back and use the differential equations, and you may not have an analytical closed form solution. Okay, you might need to do numerical methods, you might need to apply p-spice, and the such. Okay, so let me tell you one last thing before even we do any solution is, this is just insight. We are assuming a solution of the form e to the power j omega t plus phi. this is what we're doing is we're assuming this as the solution. When we use this as a solution, we have a cos omega t plus phi, and we have also an analog sine omega t plus phi. This is j. This guy is equal to this guy plus j, this guy. That is why when we assume this guy is a solution, we take the real part. Remember in the phasors, we have to take the real part. That's what we're doing, really. We're actually assuming a general solution of this form, doing what we need to do, and then when we come up from the phasor domain, we are getting this response under the real part. So you have to realize that this is we initially assume a general solution of cos omega t plus j omega t plus whatever phi. Then we do whatever we have to do. Then we come back from the phasor domain to the time domain by taking the real. So this is one of the very rare examples in life where we can't solve a specific solution. We in fact try a general family of equations, do what we need to do, and then come back and reduce it to the real part. So really this is what we're doing. You have to put that in mind, why this mechanism works. But I'm not here to talk about this. Maybe a professor is going to lecture to the details of why that works. But right now, let's just get into examples, and that's what you guys came here for. So for this example, you're told to, for example, find what is the voltage at this point. So step number one is very easy. What you do is you have to convert all sources into phasors. That's why we study phasors. So you take a sinusoid and convert it into a phasor. In this case, there was a 20 actually. So how do you convert this guy into a phasor? Anybody? We discussed this before.
So omega is 4.
Yeah, omega is 4, but what's the phasor representation of this guy? You guys remember? No, phasor representation of this guy.
Yes, it would be 20 angle negative 15.
Excellent. Very good, very, very good. And mind you, if you got this guy as a sine, do you remember those?
You have to convert.
Exactly, you have to convert. So to convert from a cos to a sine, just even write this down very quickly. Cos to sine. I'm just going to write argument. You do what? You do argument minus 90 degrees. I'm sorry, sine to cos. That's why we need to go. From sine to cos, it's argument. Then another thing is you put a minus sine or a minus cos, whatever the case, to get rid of the negative on the outside, you do a plus or minus 180 in the argument.
Well, from negative sign, we'd have to do argument plus 90.
No,
to get to cos, from negative sign to
yes,
cos.
exactly. I forget. This just apply to two of them, right? Negative sine to cos is just plus 90 degrees in the argument. Just remember this and know how to do it. So we got the phasor representation, bam, we're done. The second thing is you find the impedances in the circuit. The question is you need to know what the operating frequency is. What's operating frequency in this case? What's omega? We need to know what omega is before we can find any impedance. What's omega?
6.
Omega is?
Oh, omega is 4.
Omega is 4. So omega is equal to 4. Why? It came from the coefficient of time in the argument of the sinusoid. So then now we can find this. What's this guy? What's the impedance of a capacitor? 1 over what?
1 over j times 4.
Oh, j omega c, exactly. J omega c.
Or we can say, what's up?
J omega c.
Oh, yeah.
Yeah, so 1 over j. What's omega? Omega 4.
And then 10 times 10 to the negative 3.
10 to the power. There's no.
C
Yeah,
is
you're
that.
right. You're right. You're right. And
So
exactly.
you can also say j over negative j, negative j over.
Negative j, and in fact, we just like leaving it out. So we got this guy. The Henry is j omega L.
And that's 10 to the negative 2.
Yeah, 10 to the power negative 3.
Negative, because the thing like itself is 10 already, so 10 times 10 to the negative 3.
Well, there was 4 times, yeah, well, you just write it down. 4, in fact, let me just write it down very well. Sorry about that. So capacitor 1 is equal to the Z of capacitor 1 is equal to what? Is equal to 1 over j omega c, which is equal to negative j of omega c, which is equal to negative j. Omega, we saw it was 4 times 10 to the power. Because this is 10, you're right,
10 times
10, negative 2. You're right about that. There was a times 10. Thank you for pointing out. For the inductor, Z for the inductor. So what's that? It's like that's H1. It says what? For L1. Use L1. Is what? J omega L, which is what?
So it's j times 5 times 4.
10 times J. Oh, okay, there was 5. Sorry. 5 times omega 4 times J. 20. And then that's about it. And then so if you do this guy, you will get this guy is actually equal to negative 25. And then this guy is equal to J, 20, and this is of course J. You do this. Okay, once you transform to phasor, and you got this guy, and you got this guy, you're done. Why? Because somebody asked you to find what's VO. Let's see what VO to be what. Let's apply nodal analysis. VO, what's this? This ground circuit, remember? That's how we always do, the ground circuit. So VO minus this is what? VO minus this divided by what? What's the impedance of this guy? The impedance of this guy is what? Minus 25. So VO minus 0 over minus 25J. Plus, can someone now give me the next one? VO minus what? We're doing nodal analysis. We're doing nodal analysis. So what do you
0 over
VO minus 0, right? Over what? What's the impedance of the
20J.
20J. 20J is the impedance of the inductor, as we found out. And then VO minus the voltage source. The voltage source, we don't take the cos, so let's take the phasor. So we VO minus what?
20 angle minus
20 angle minus 5, 50 minus, what is it minus 5? Minus 15 degrees. Over what?
60.
Over 60. And we said this is what?
0.
0. You take this guy, and you, if you do this guy, you solve using a calculator or use all the steps of complex analysis, you would get VO is equal to VO very quickly is equal to okay, VO you got is equal to 17.15 angle 15.96 degrees. You get this. Now the question is now, is this the final solution? No, because the problem is we are told we want to find they give you already the voltage source in form of time. And you want to find what the voltage is. It should also be a function of time. This is what? Is this a function of time or is this a phasor? So you have to convert a phasor to what? A function of time. So how do we do that? We write V, let me just put him in a scribble to show this is a phasor. So we're supposed to convert a phasor into a function of time. So V as a function of time, VO as a function of time is equal to take the phasor and convert it into a function of time. So you're going to have to write, now you could ask me, omega t, we're supposed to have an omega t, right? The omega t, we take the one from the voltage source. So we take WT. Always we do this, because this is what's exciting the circuit. So we have to, it operates at this frequency. So we take omega t. But then the phase, we don't take the phase. We don't even care about this phase. We take the phase of what you got. What's the phase? What's the phase of this phase? What's that? 15.96. And then the question is, what's the amplitude?
17.
17, so you have to put 17. In this case, cos. So this case is equal to cos, and this is 17 as amplitude. So equal to this. So 17 cos that guy. And that's your final solution. That's a steady state solution of the circuit. So things now should look very clear. Now, we have covered nodal analysis. We can do the same thing very, very quickly. I just want you guys to get comfortable with what's going on. And I'm going to require you guys to participate in giving like, the answers as we go along, because I'm sure most of you guys are very, very familiar with nodal analysis and mesh analysis under the DC case. So I want you guys just to get comfortable with this next one. This is going to be very quick. So we've got a plus, we've got a minus, we've got this guy, and we've got this guy. And then okay, this circuit here. You give a plus, you give a minus, and you give a. In this case, they made it easier for you. They gave you everything in phasor. If they didn't give you things in phasor, they give you things in time. Then you're going to have to do the conversion yourself. In this case, we're just going to give you everything to make your life a lot easier. You got an inductor is given in phasor form. This guy is going to be I have a question for you guys. In this problem, they gave you all the impedances, right? Of all the components, right? But the question is there any way you guys could find the operating frequency? This could be a trick question actually in the final. Is there any way you could be able to deduce the operating frequency based on this problem? Although this is not the question that's being asked, but as a challenging question, could you do it? Is it possible to find the operating frequency? No? Why is that? Why is it not possible to find the operating frequency? That's the question you need to ask yourself, why?
Well, the problem is already given in the frequency domain.
True. It's already given in the frequency domain, but the question is, can you find the operating frequency of this circuit? Is there any way to find the operating frequency? How would you try to find it, actually? Is there any way? I'll leave you guys to think about that question. Okay? Next time we see each other, you tell me if that's possible. Okay? And another thing, this is an insight that you guys may not know. If, let's say, a student does nodal analysis, and they get the voltages, let's say V1, V2, V3, for example, and they find all the voltages. Then another student does the same nodal analysis, and they got a solution. And then somebody says, is it possible that they might get different like numerical solutions for the nodes, but they have the correct answer? Is that possible? Is it possible? If, let's say, okay, let me phrase the question again. If the students use a different, let's say one student uses a reference here, and another student uses a reference here, will they get different answers? Do you think under nodal analysis you get the unique answer irrespective of the reference that you make? Do you think that's intuition so far? So far, you've taken this class. If you think you change your reference, are you going to get different node values? Is there a chance you might get different node values but still get a coherent solution?
Yes.
Yes.
From that particular node, yes.
Yes. So if you take a reference and you take a different reference, there's a high chance that the nodes and voltages that you're going to get are different.
Well, even if itself, 0 would be there. If you move the reference to 0, it would be at a different node anyway.
Exactly. And the question is, how would you take a solution of one student and take a solution of another student and see if they're actually the same? How would you do that? How would you know that if this solution is actually the same as another solution? How would one do that?
Some type of equivalence where we find...
Exactly. And how would you find the kind of equivalency?
We shut down our sources and find the equivalence of each component, or...
That's one way.
That's
one way. You could find the Thevenin equivalency of the circuit. That's one way.
Could we saturate the circuit as well and find like infinite, to find short and open lines?
But that's Thevenin equivalency.
Yeah.
When you do that closing of the circuit, that's Thevenin. We haven't got to that point, but you're right. There's one way to do this to find the Thevenin equivalency.
Subtract two nodes.
Perfect. That's a very good answer. In fact, this should be when a question in the final, but if somebody has a solution and another student has a solution, you realize that every node is of the general form. Let's say you got a solution as A, and you got your B, and you got your C, and you got your D. The general family of solutions is what? A plus C plus C plus, C is like a fixed value, so plus C plus C. So if you've got another person has another solution, all you have to do is just make sure that if you take this guy and you subtract, as he said, and you take this guy and you subtract, you should get the same value. So that's one thing you should think in the back of your mind when you do nodal analysis. Most students think that nodal analysis always gives a unique answer. It's not true. It depends on what you call your reference. So in this case, sorry for that aside, but because I have some students who think that they come to me for, if they were to complain for a problem, they would insist that that node value is a value that should be correct, irrespective of where they put the reference. And that's not true. But anyway, that's not the point. The point is, let's just continue with this guy. And the question is, use nodal analysis to find the voltage across what? Let's say you need to find it wasn't said. Okay, V1. Where's V1? V1 is, yeah, we're trying to find V1. Okay. And the question is, how do you find nodal analysis? How do you do nodal analysis on this circuit? Let's go. But it's not, I need your participation for this part. Everything is given to you. Phasors are given. This is the current. In phasors, you're given the impedance of all the components. This is 12 ohms. That's 4 ohm. That's a phasor. The question is, this code is V1, okay? This code is V2. And usually we make the reference the one with the highest number of nodes, and we just kill it to 0. Okay? And the question is, how do you do nodal analysis? This is an example of a supernode. We just covered this. We just need to do this. This is a supernode example. So how do you do that? This is V1, that's V2. Yeah, I need you guys to give me the equation.
For the supernode would be the V side, the positive side minus the negative side.
So
for the supernode, are we going to do?
So what's the supernode, first of all? It's
So we include the two nodes and include the power source with the phasor.
So you want to do this? Is this the supernode you're saying? Is that what it's saying?
Well, in our notation, we would not include the 4 ohm in the supernode. We would just come around the
Could you include the 4?
You could.
You could.
There is a way, but I think from the way we have learned it through the lectures is not to include any of the resistors within the supernode.
Okay, the reason why the supernode works, if maybe in the future I could explain that in detail, but the reason why we have this abbreviation as supernode and we made all this stuff is because we don't want to analyze the current that goes through the voltage source, because it's the same current that flows backwards. I mean, the same flow, so we want to sort of contain a closed loop operation, and we don't care much for this current. In fact, we can't, it will add an extra parameter to our equation, but you have 2 equations, so we cancel that out. So we don't need it. We don't need that. So we just assume this is a closed loop, and we go V1. Let's at least apply it. Let's apply it to go V1. This is a current source. So V1 minus what? Ground. V1 minus ground over what? Over what?
Negative
3J. But everything is assumed to be in ohms, both the real and imaginary components. So we can just ignore the ohms for now. And then what's the current that's going in? This guy. 3, yeah, 3. And it's just, let me ask, what's 3 phase 0? What's this? Just 3, because it's just 3. So it'll be here. The phase is 0. Just divided 3. So it's 3, or plus or minus? Minus. Huh?
Minus, it's going into the node.
Excellent. Going to the node is minus 3. Minus 3, and you should put a phasor because to show that this is, it doesn't make a difference actually, because any real number in the complex domain is
That would just be 3 cos omega t.
No, for now we're not dealing. We are dealing with phasors. This is what again. The reason why I don't want to spend extra time on this tutorial, because I could speak here for days, but I think I feel guilty about this. What I should really have explained is why we have the phasors and what's the reason why we don't have the time to be dependency here. There's an explanation for this, but it just me need to explain for longer. I need to explain. I need to have more tools to explain that. But really, the idea is again we're going from. We're assuming a solution, a general solution of the form e to the power j omega t plus phi. We're using this guy, and the real part of this guy is actually cos omega t, which is what's the real. This is a real input into the into the voltage sources. But we're assuming, hey, we can't solve this. This is difficult. Okay, we can actually solve this using differential equations, and we get an answer, no problem. We can even find using the time analysis. We can even find a much more richer solution with the transient response. We could do that, no problem. That's not what we're doing. We're saying, hey, let us assume a complex exponential as the basis solution. We take it, and once we solve this is now the solution of the complex exponential. This, right now, what we're doing here, we're simultaneously finding the solution where we have a real and imaginary part. I mean, we're simultaneously doing this. When you're doing this operation, we're actually assuming a complex exponential. It's when we're coming out of the phasor domain into the time domain that we are taking the real part of our, you know how we take the real part of our solution? That's how we find the response to the system under a real value, which is cos omega t. So I don't want you guys to confuse this, what's going on. Why do we have this complex domain? Why are we moving into this domain? You have to understand these reasons, what we're doing here. You know, yes, this is not a complex, I mean, cos omega t is not a complex number. This is a real valued function. And you could ask yourself, why are we doing this? Well, we are solving the general complex exponential as a basis function. Once we solve it, we're coming out. Once we come out, we're taking the real. So you know how we take the real part of this game? That's the cos omega t.
No, but I was just wondering if we were given this in its function form, in its cos function form, and asked to convert to its phasor, assuming that it had a phasor, yes?
No, the phasor is just a tool. It's a tool. The phasor really.
But if we weren't given this, if we were given, would we be able to get a phasor from an equation, from a function?
From a function, like, give me an example.
Like if we had 3 cos omega t, could we produce a phasor from that, assuming that
that's what you did.
Plus 0? That's what I was saying. If we assume that it would then be 3 cos omega t plus 0.
Yes.
This would be its phasor representation of
this
that function.
it is.
That's all I was asking.
You're right, 100%. But you have to understand that the phasor is just a dummy variable.
Yes, yes.
And then once we're just using it to solve actually a much more general problem, but but surprisingly is easier to solve.
Right.
And the reason for this is because when you take a differential, when you take a derivative, when you take an integral of an exponential function, what you're doing is basically when you take a derivative, you are taking the argument of the function or the coefficients of time and you're just multiplying it before. And if you're dividing it, you're dividing by the exponential. So it's a linear function. This is a linear circuit, so that's why this works, this idea technique works. I want you guys to be all the time remember that this is a steady state response A. B, it does not work out if the input sinusoids are not sinusoids. Okay, and if it's DC, you know how to deal with DC. So DC would be under omega equal to the frequency is 0. So if omega equal to 0, you're dealing with DC. Okay, and that's of course e to the power 0 is what? 1. So you're dealing with a constant. So when you're dealing with a constant, you know how to do the DC. You covered that in the previous chapters. If you're dealing with non-DC, and you're dealing with a sinusoid, this works. If you're dealing with a rectangular pulse, no. You have to use differential equations. So, okay, so getting back to this guy, we were just over here. So we minus this guy, the terminal. Yes, you could do V1. Do we do V1 minus V2? Do you guys do that?
Not yet.
Okay, so.
Oh yeah, we do that.
Yeah, so you guys cover that in class, right? Okay.
Yes,
Yes, you could do that, that's right. So V1 minus V2 over what? Over 4. And then this is the KCL at node V1 using nodal analysis. Now let's do KCL at node V2 using nodal analysis. So what's that? And you guys give me the answer.
Which one? V2?
This is not even done. This is actually the supernode is
continuous.
It's continuous. It's not even done. Actually, to be honest with you, it's actually best to get, because the reason why we can get rid of this is because when you come into this part, we're going to do what? We're going to do V2 minus V1 divided by 4. Doesn't that cancel? V2 minus V1 over 4. I mean, because this is still one doing plus, right?
Yeah.
We're treating this as one supernode. So what happens to these two guys? They cancel. That's the reason why we always put a circle around it. This is just proof, right? But anyway, let's continue. V2 plus what? Plus V2 minus 0 or what?
Over J6.
J6. 6J and J6 doesn't make a difference, but by convention, you raise a good point, you always write J6. V2, next one. V2 minus 0 over 12. When you do this guy, and this is basically, okay, let me ask you, this is, how many equations is this?
One equation.
Well, this is one equation. How many unknowns?
2.
This is 2 unknowns. Can this be solved?
No.
No, so we need a second equation or a second relationship to solve this. How can we do this?
So it's V1 minus V2 equals 10.
Excellent. V1 minus V2. How we do this is because if we start from V1 and we reduce by a potential difference given by this phasor, we're going to get to V2. So from V1, we minus 10, this guy, we get this guy. So V1 minus V2 is equal to 10, 45. Now we have this second equation. We've got two unknowns, V1, V2. If we solve this guy, we're going to get V1 is equal to, this is maybe you guys can go try this out. The reason why I'm not going through these steps is because this is something that the calculator can do very easily. So V1 is equal to, here according to this guy, V1 is equal to 25.78 negative 70.48 48 degrees. Okay, you can go try this at home. That's V1, yeah, 25, yeah, that's right. And we get V2, yeah, that's V1. And V2 is equal to 31.41 angle negative 87.18 degrees. That's what you do. You get as your answer. Again, these are phasors. This, again, I can't emphasize more, is a solution to both imaginary and real components. So if they give you a source, if they give an omega, an operating frequency, WT plus 5, and then they told you to find the response of V1 and V2, these are the phasors. And this is not the time domain representation of the solution. For you to find the solution, you have to convert this. If let's say they gave you to convert that, they told you to convert this into the time domain, you would take negative 25 degrees 0.78, and then you do cos what? Omega t plus what? Plus that phi. This phi is equal to this, the phasor. The phasor is phi. And you would do the same thing. This will be the complete solution, the real solution. In fact, the solution to the excitation under a real function. Okay? So I don't want you guys to confuse those two concepts. Okay? So don't think that when you go to the phasors, that's the right solution, unless it's specifically asking the question, that's not the final solution. That's the solution under e to the power j omega c plus 5. Okay, so the last one. In fact, you know what? I'm going to skip mesh analysis. The reason for this is because I think you guys are already comfortable with how this thing works. Right? I think you guys got the idea. Yeah. So I'm just going to do one problem that cannot work under DC. It's the last problem of the day. Okay? And it's in fact, I believe is the most powerful method in the course. Why? We applied the reverse superposition principle because we took a complex exponential and we got the excitation of the system under a sinusoid. We actually used that principle, the superposition principle, but we used it in reverse. We said, hey, we can't solve the real part of a complex exponential, let us try the complex exponential. We take it and we excite the system under the complex exponential, then we take the real part of that complex exponential, then we got the cos. I mean, that's what we did. So we did the reverse of the superposition principle. Now, we're going to use a variation of the superposition principle, the one that you learned in the previous part of the course, and the DC. I mean, we gave you a problem, and it had multiple sources, and the idea we shut off every source, and we see the contribution of each source, and then we use the superposition principle to add whatever voltage or whatever current is of interest, and to see how the system behaves under multiple sources. This is the whole idea here, what we're doing here. Again, let's try this superposition, but for mesh analysis, this is a very good example. Okay? Now, for this problem, actually there's only two ways to do it. In my knowledge, just my knowledge, I may be wrong, but according to what I understand so far, there's only two ways to do this problem. Using the superposition principle and using the transformation. And not all problems can be done using the transformation principle because it depends on how convenient the circuit is. If a circuit, for example, does not allow you to use you're supposed to have a voltage source, an independent voltage source, with resistors in series for you to start the conversion, or you have an independent current source with a resistor in parallel for you to use the transformation method. But that may not be the case. You could have a problem that does not have that. Okay, like for example, in this case it does. For this case it does. Okay, but in fact, if it does, if it can be solved using superposition, I want you guys to go do it on your own and verify the results. But usually, you cannot get a convenient sort of orientation of the network that it may not even allow you to do the transformation. But something that's going to work all the time is the superposition principle. Now, the superposition principle, most people don't like it, is because you're solving the circuit n times, where n is the number of independent sources in your circuit. There's a 4 ohm here. This is the last problem we're solving. 4 ohm, the 1 ohm here, and then we've got a 2 Henry. And we've got V plus here, and this is 10 cos 2t volts. And this guy is 22 sine 5t amps. And this is the voltage of interest, VO, V minus. Give a reason for ohm. Yeah. And then the problem, the question you're being asked is, find for us the voltage across this resistor. What do you notice, first of all? Does anybody see anything that is crazy already before we continue? Is there anything about this circuit that's a bit strange?
No phase shifts.
Hmm?
No phase shift.
No phase? No. Well, a circuit is allowed to have no phase. When the phase is zero, it just means the phase is zero. I mean.
We have to convert the sign though, so it'll do it.
Okay, step one, very good. So step one, we notice that we don't have the same basis function. I think, I'm not sure about this, but I think if you change this guy to sine, and you did the whole thing, and you took the imaginary part, you should get the answer. But try it out. But we always use cos as the customary procedure. So we have a cos. What's the sign? How do you change the sign to cos? Remember, this is a positive. There's no negative outside. It's just a sign. So what's in your mind? What do you think?
5t minus 90.
Minus 90. Excellent, guys. So the 2 sine WT minus 90 amps. I remember he said there was no phase, but not now. We found the phase.
To be close on it, wouldn't it?
Cos, you're right. There's a cos here. Sorry about that. So that was step one. So we took out this guy, and the t was what? Was 5. Was 5. Right? Okay, that was step one. But there's still something else wrong with this circuit. I want you guys just to look at it and tell me what's wrong with this circuit.
Do these have frequencies?
Excellent. This circuit is operating under multiple frequencies. Look, we have 2. Omega of 2, omega equal 2 here, omega equal 5 here. Omega is equal to what? Omega is what?
What is that?
Just 5 volts. What's this?
0.
0. This is DC. You know how we wrote this? DC exactly. It's a DC circuit. It's a DC. This is 0. Omega equals 0. And then the question is, that's being asked to us, is now, can we solve this circuit? Well, do you think mesh analysis, nodal analysis would work on this circuit? Why not? And there's a reason why we can't apply nodal analysis.
You can't mix the DC and the AC.
Why not?
The equations won't allow for it.
Forget about the equations. Let's try. Let's just see. Let's see you try to do it. Well, let's
One is changing and one is consistent. It's constant. The DC would be offering a constant, whereas the AC would be changing under that in that domain.
Maybe you may be right, but yeah, I don't understand. I apologize for that, but let us say you're trying to apply nodal analysis. I'll just give you an example. When you try to apply nodal analysis, remember step 1, you're told to change everything to phasors, right? Remember, okay, let's do the phasor representation. What's the phasor representation again? What's this? 10 what?
Angle 0.
Angle 0. And this guy is what?
2 angle 0.
2 angle.
Negative 90.
Negative 90. Very good. And then what's this guy?
Nothing.
5?
Oh yeah.
Or just 5.
Wait, no, is it 5? It's just 5. Is there any omega?
There's no.
There's no. In fact, does this guy have a phasor representation?
No.
No. It's DC. So we leave it as this. Because if you put the phasor representation, then if you do allow that, then your back of your mind you have to say it's a phasor but under omega equals 0, but nobody does that. Because you wouldn't know, you would have lost that information because omega is 0. So you just leave it as 5 volts. This is DC. Those two are operating at 2 different frequencies. The question is, when you apply nodal analysis, you're going to run into problems. Because if let's say you go V1 and you apply this and you find, let's say you find V1 is equal to, let's say you do nodal analysis, you find V1 is equal to 10. First of all, you made a mistake. This is operating at one frequency, this is operating at a different frequency, and if you apply nodal analysis, you're saying, hey, this guy is operating at the same frequency. This is what you're saying when you're using it. But let's say you did, let's say you used it, and then you got V1 and V2. Already a mistake in the beginning, but let's say you went ahead. Then now you wanted to convert this guy as a final solution. You will get a phasor. To take a phasor, to convert the time domain, you would use what? Omega t. What omega do you pick? Do you pick this 2 omega? Do you pick this 5 omega? Which one do you pick? You can't. So you already know this. Since there's ambiguity, that's wrong. So the only solution would be the superposition. So the superposition actually shows its muscles on the multiple frequencies. In fact, it's probably the only way to do it if the source transformation is not convenient. Source transformation could possibly do it because when you do a source transformation, you're dealing with one source at a time. So you can take it, apply, you could possibly do it. But I think the only way to do it in this case would be superposition. And it's always, every time you see multiple frequency operation, always apply superposition principle. It wasn't that useful in DC, but very useful in the AC. So let's apply this guy. So for us to do this, what we do is, I'm not gonna go through it because we're already almost out of time. And what I'm just gonna do is I'm just gonna give you intuitively how we do this problem. So under step 1, we just assume that this guy is the only guy that's operational. Let's assume. This guy is always on, this guy is on. So this guy is on. Okay? So this guy will be what? Off. This guy will be?
Sure.
Off. Yeah, off. Off. But off, I'll get to tell you what off is and what on is. When this guy is on, this guy is on. So we can just copy it down. And we can copy the what? The phasor what? What's the phasor that we copy? We copy this 10 phasor. But then you also make sure that you write what omega is. It's important that you write this. Omega is equal to what? 2. Because when you come back, you're going to use 2. Okay? And then now, a current source. How do we kill a current source? Anybody have any idea to kill a current source? How do we do that? How do we kill?
Open line.
Open line. That's the only way for the current not to go through, to make it open. Right? So you have an open line. Now we're dealing with what? Steady state solutions. Right? Steady state. Sinusoidal steady state solution. So we're looking at the solution where time is sufficiently large, larger than t dash. So the transient components have died. So meaning every capacitor has saturated and every inductor is behaving like a resistor. This is what you're trying to say after sufficient large time. Anyway, as we get here, we now see this is a resistor, fine. A resistor does not change, right? So we just have the resistor here. This is what 1 ohm. In fact, this is the point of interest we're going to be examining. So let's say call this plus and minus. Anyway, and then we come here. What happens to the capacitor after sufficient time?
Saturated, so it's open line.
Open line. It's open line. So this is an open line. Okay, and and by the way, this omega is very small, at least 2. Okay, remember it will be a different story under high frequency. Remember how before we talked about high frequency? Omega is just 2. If you're talking about 10 gigahertz or something like that, in fact, even this course, all this breaks down. You deal with much more richer Maxwell equations. You can't solve using this analysis. But this analysis assumes very small frequencies. So anyway, let's proceed. So you're right. After steady-state solution, the capacitor behaves like an open. So we have an open. Do you have any inductor?
Yeah.
Sure.
That's
I'm
2
sure.
Henry at the beginning.
Yes. This inductor was supposed to be open or short. Short. Why is it short? Because the inductor after sufficient enough time behaves like a what? Like a wire. Just like, yeah, short line. That's true. So then here was what? We were open because the capacitor. Because again, remember we're always dealing with steady state, right? So after time is big, and then this is a 4 ohm, and then this guy is what?
Short.
Short. We always short voltage sources because that's the only way we can make V minus V, and which is the same, which is 0. So let's say it was 10, this was 10, 10 minus 10 is 0. That's the only way you can make the potential 0. So that's why you need to short. And you go like this. Then, okay, this circuit is very easy to solve because now this is a 1 ohm, that's a 4 ohm. Is there anything? This is we're dealing with. Sorry, all this time I said that this is not under this. This is under. This guy even will be a short. This was under what? Sorry, this was under what? Under the 5 volts. Remember I talked about the short of. This was under DC. We say that a capacitor is short under DC after steady state. This was DC.
Oh,
This was DC, not under the 2 ohm. My mistake. Okay, my mistake. It was under the DC. We can only say a capacitor is short under DC after sufficient amount of time. And an inductor is like a wire. This is DC only. DC. Please don't confuse that. Okay, so we do this. When we do this, we're supposed to find, for example, what the voltage across this is a resistor. So what you do voltage division. You take this guy, divided by, so it will be 1 divided by 1 plus 4 ohm times what? Times 5 volts. And then you get, but the problem is the orientation is giving us plus minus, so what would you have to put as this voltage here, this contribution? What's the voltage here? If this is plus and this is minus, you're forced this to be plus and minus, what does this have to voltage be? This is 1, actually 1 volt. So what do you get? What's this value? Do you put 1 volt or minus 1 volt? Minus 1 volt. Because we've changed, we've insisted this is plus and this is minus. We've changed the orientation. So you do this for the 5 volt. The question is now, the second thing is, that was my mistake. That was a very bad mistake, actually. So you did this, you took care of this guy. So this guy is done. Now we want to see the contribution between these two reference points under this voltage source. So how do you do under this voltage source? Okay, now we still have an inductor, right? This is what? An inductor. The inductor, what is the impedance of an inductor? What do? We multiply by what?
JWZ.
Or
JWL.
JWL. Okay. Do you remember how in the previous example, if let's say you forgot you're dealing with DC, under DC, what's omega? What's omega under DC? 0. So you put omega equals 0. 0 times J is what? 0 times L is 0. So your resistance is, impedance is 0. That's actually the definition of DC. So if you forgot, you would just work out for you. Anyway, so for this guy it will be J omega C, so it will be, let's call it just Z1 as a block, which we will know. And we told you is equal to J omega L, which is equal to 2 Henry times 2 times omega, which is 2, and L is, sorry, 2 is the L, and it's a J. So J 2 times 2, okay? And then we have a voltage source here, I mean a current source. What happens, should this current source be on or off?
Should be off, but I don't know, is that how we do it for?
Yes,
either way?
always.
Yeah, so off. So
Off,
it's
off, off. So off should be what? Should be open line. This guy, this is just a 1 ohm resistor. Does it change?
No.
No, it's a 1 ohm resistor. The capacitor, does it change? What happens to the capacitor? What's the impedance of a capacitor?
1 over JWC.
Exactly, so J over WC
Negative,
negative.
yeah.
Yeah.
Negative
So,
J over
yeah,
WC.
exactly. So we have that. So you know what's W? You're operating at what frequency?
2.
2. So W. What's C? 0.1. Okay, whatever. This guy is this guy. And then we go on. Okay. And then we apply the same thing with this guy. 5 volts. 5 volts. What happens? How do you kill this guy?
Short.
Resistance.
I mean, there'll be there'll be a resistor here, and this guy is short, right? So it'll fall. So you do this. You've got an impedance here, you've got a resistor here, you've got an impedance here also again, another impedance here. And the question is now we try to find what? We're missing also a resistor 1 ohm. Sorry, my bad. But this is the 1 ohm. Sorry. Sorry about the mess. So the question is we're trying to find what the 1 ohm is. So you would use what? You would use. You would take this guy, for example, combine them together in parallel. You multiply them. You know those rules like R1, R2 over R1 plus R2 in parallel? They actually work out in this case. You can actually use Z1, Z2 over Z1 plus Z2. I mean, it's the same thing. It's just a analog. It works out the same. So you can do that to find the impedance in parallel. You get that guy, and you leave it as is, for example. Then the question is, you want to use this guy, use voltage. Voltage what? Voltage divider, because you take again that impedance divided by the impedance plus 1, and then you would get sorry, no, in this case you just, actually, you know what, it doesn't make any difference, just apply KVL, or you could apply KCL at this node, KCL at that node. You've got 2 unknowns, you have 2 equations, and you can solve. I mean, it's just the same thing that we did before, like nodal analysis. You can use nodal, you can use mesh, it doesn't make a difference. Just do it and you'll be able to solve it. Then when you do this, you're going to find a contribution. The contribution is going to be what? Let's just say the phasor was V1, phase 1. Just give an example. I mean, you could do all these complex numbers and you get this phasor, okay? Now, how do you find how do you change this guy into the time domain? What should it be? To what?
This would be V1
V1 cos what?
cos omega t.
What is omega?
2.
Oh, 2, yeah. 2t
Uh-huh.
plus whatever that is.
By 1, right? You do this and you have this aside, okay? And this was under the assumption that this was a plus and a minus, right? Okay. So then now we go ahead and leave this guy as is. We leave this guy as is. We leave this guy as is. Before when we calculated it, I don't remember, it was what? 1 volt, right? Negative 1 volt. Remember under the DC excitation it was negative 1. So it was negative 1 under this guy. This is under this guy. Then now we repeat the same procedure with under this guy. That's only being on. When this guy is on, just very quickly, what happens to this guy?
Short.
Short. What happens to this guy?
Short.
Short. What happens to this guy? What's the operating frequency?
Same thing.
What's the operating frequency? Not same thing. What's the operating frequency?
We're changing that. It's 5.
5. 5 omega is equal to 5. So you apply 5 times.
But it's the same equation as we did for the other AC, where it's 1 over J.
Exactly. So you do 1 over J omega C, you find the impedance here, you find the impedance with here, and you find the impedances. And the only thing that's going to be on is this guy, and this is going to be a phasor, and you apply the same nodal analysis. And the only thing, let me see, that's going to be changed as much, the only thing that's going to change is just it's going to be killed. But everything else remains, and again, the impedance is a function of omega, so if you're using 2, you're going to have to use, not the 2 omega, but use the omega of the cos, so use the 5 omega. And here you use omega here, 1 over J omega C, you use this 5, make sure you use this 5. Then you solve it, and then you find what is the voltage across this guy. You could use KVL, KCL, whatever, and you're going to get, let's say, V2 is equal to, you're going to get V2 phase V2, for example. So how do you find this in the time domain?
V2 cos 5t plus
5
omega 2, or 5t.
5 2. Excellent. So you got this. Now the question is now, what is the solution under VO minus V1? What's a full solution? The full solution is going to be, let's say, let's call this VO, okay? So VO is equal to, remember the negative 1? Negative 1 plus V1 cos WT, 2t plus 5 plus V2 cos 5t plus 5 2. Now, you realize something. There's something as a check that you actually did the right solution. Look at the, remember the different operating frequencies? They appear again. When you have a solution that has different frequencies, then you know you're good. You're good. But sometimes it's quite possible, I don't want to get this wrong, if your phasor was 0, then what does that mean, if your phasor is 0? If you got, let's say for example, you got a VO and the phasor was 0, what does that mean? What would you even have a cos? No, because even if you got a 0, you take a 0. What is the idea? We take a 0 and then we say times cos, whatever the operating frequency is, but it's 0. 0 times cos is 0. So when you see this as a check, always make sure that if you see that your terms, if you found out that your phasors were not 0, then you should expect to see terms or excitations that have the multiple frequencies of the original problem. That's always what you do. Okay? I hope this helps. In fact, I believe this is one of the most important things in the course. And everything, the V Thevenin and the Z Thevenin and the V Thevenin and power maximum, all these things are just like they were in the DC case. There's only one difference. The only difference that I'm just going to give the output for you guys, maybe when you're going home or you're thinking about this and to try to memorize as time goes by, and I'm not even going to go through the definition. What I'm just going to say is this. This is going to say is that for average maximum power transfer, we say that the Z of the load, or the impedance of the load, is equal to Z Thevenin but conjugate. Okay? So we take and the reason for this is, I don't know if you recall this, when you took the power of your load under the DC case, you found the power as a function of RL, and then you took a derivative with respect to P to RL, then you set equal to 0. But the proof is not fully conclusive because your textbook is supposed to have taken a second derivative and substitute RL to find negative value, but forget about that for now. And you took it equal to 0 and you found the critical point was RL 0. And this happens to be the real part of the impedance. The real part of the impedance doesn't indeed equal to the real part of the impedance, or Thevenin impedance, so of the load. So the real part of the Thevenin impedance is the same thing as the real part of the load impedance. And that is true. This is satisfied and that works out well. Nice. But then when you go to the complex domain or the phasor domain, you realize it's a conjugate. And the reason for this is actually you'll be solving an equation of the form P Z L. So you're taking the power as a function of the load, and you can't take a derivative with respect to ZL. It's not that easy but what you do is we take this guy and we take it with respect to d R L, and then we also do another equation where we do, because it's two-dimensional space. So we take it, P, the derivative of power with respect to ZL with respect to XL. XL is, I don't know if you can recall this, the impedance. It is the imaginary part of the impedance. Okay? When you do this, coincidentally, I mean it's obvious. When we do this, we get the same thing, and we're going to get, yes, RL is equal to R Thevenin, right? Let's say we've got ZL is equal to RL plus X, what? L, right? And what is this is the impedance of the load. The impedance of Thevenin is what? Is written as Z Thevenin is equal to what? R Thevenin plus X Thevenin J. This is just the impedance, the way of writing the impedances of the Thevenin and the impedance of the load. Now, in the DC case, we found RL equal R Thevenin. RL is equal to R Thevenin. Fine. And in fact, this was true because it had to hold, because if, let's say, if our X Thevenin and our L Thevenin were all, our XL and our X Thevenin were all 0, then it would be this special case, which would be the DC case. That's why it has to hold. Okay, that's fine. But the problem is, that means this equation was done, and it was the same sort of optimization problem. But the second dimension is when you do this, you find out that XL is equal to what? Anybody guess? XL is equal to what? What X Thevenin? Is it equal to X Thevenin? Just like that? XL is equal to X Thevenin? No, we find that it's equal to negative X Thevenin. So it was just the same problem. I don't know if you can recall the optimization problem. We took a derivative with respect to one dimension. In the phasor domain, we do an optimization problem with respect to two dimensions, that is the real and imaginary parts. And we could find out, it's out of rigorous mathematics, but when we find out that the real load has to equal to the Thevenin load, and the imaginary part, or the reactance, the load reactance is equal to the negative of the Thevenin reactance. That's what you get. And hence, another way of summarizing this is just to say Z Thevenin is equal to Z load, so you do conjugate. So if you take the conjugate of the Thevenin impedance, you will get a load impedance that maximizes average power transfer. So if, for example, you got a very complicated AC circuit, and then somebody says, okay, I have a device, I've got a network that's maybe plugged onto this wall, and then somebody says, can you please find, can you construct a load impedance such that you can draw the maximum power from an adapter? So that's a problem, an engineering problem that somebody can present you with. And the only way to do this, one way to do this would be to say, hey, let us find the Thevenin resistance of this device as produced output, and then we take the complex conjugate. And then you could ask, how do you construct? Okay, then let's say we did find out, let's say it was 3 plus 5J as a Thevenin. I'm just giving an example, okay? Let's say it was Z Thevenin, okay? It was given to you as a design problem. Somebody gave you this, and they said, okay, so maximize the power output for us. How can you do this? You would take the conjugate. What's the conjugate? So this is the design problem now. So ZL is equal to 3 minus 5J. The question is, when you have this, 3 is what? It represents what? Or what kind of device?
Number.
Yeah, what kind of device is that? What's 3? So what kind of device is it? It's a resistor, it's a capacitor, what's it? What's this real? We're talking about impedances here, not phasors.
Resistor.
Resistor. This is a resistor. Excellent. Now you see a negative 5J. I don't know if you can recall it. Is this a capacitor or an inductor?
Oh,
If it's negative, it's a capacitor.
Excellent. Yeah, it's a capacitor. This is a capacitor. And then when you see a minus, we could actually negative J represents the capacitance, right? So now for you to find the specific value of what capacitor to use, you will have to go 1 over J omega C. Now omega is given to you because we know what is the operating frequency of the wall. 60. I mean, the frequency is what? It's 60 hertz, right? This is the power of the wall, the frequency, the operating frequency of the power that comes out of a wall. So you do, what's omega you do is going to be what? 2 pi times 60 hertz. That you get that as your omega. Then once you take your omega, you put it at the denominator, and then now you want to solve for the capacitance such that you get what? -5. So this must equal to -5. This is not known. This is a design problem to find. Omega is given because it was again 2 times 60 hertz, 2 pi times 60 hertz. J is J, and then you get the negative. And there was a J here already. So this is the 5J. So the J cancels with the J if I put the negative. So the negative cancels with the negative, we're done. Then now the omega is given to us. Let's say it's known. And now we have to solve for the capacitance. So you just take the capacitance and you divide and you get the capacitor value. The resistance is the resistance. So you would take that circuit, find the capacitor, find the resistor, and just put them in series. So you take the capacitor, you take it in series with the resistor, and you will connect it to the wall and you will draw the maximum amount of power. So that's just a design problem, one of the design problems you will get. Okay, makes sense? Okay then. In that case, let's just conclude the tutorial because it's going to be too long.